Hello everyone. Today we will review complex numbers and vectors, an important topic for engineering major and other majors. If I want to express the mass of an object, then I need one number, 75 kilogram. If I want to express the speed of a car, then I need one number, 70 kilometer per hour. However, if I need to express the velocity of a car, then I need two components to express its speed and its direction. So the car maybe is going this way. So I need to express how fast is it going, 70, 80 miles per hour, and also the direction. Is it going northeast, east, west, south? Now we need a complex number that consists of two components, real part plus imaginary part, something like this, where the magnitude of this complex may express the speed and the angle of this complex number will express the direction. Other use of complex number is to express the system response to specific frequency. So I may have a system like this one and I have an input of frequency 550 and I want to know what is the output of the system. Then the output will be the same as the input except the amplitude will change, so it will be either amplified or attenuated, and there will be some phase shift or delay. So then the system response here of this frequency will be a complex number. It may be 7 plus j10. So it has a magnitude that expresses the amplification and it has an angle that expresses the phase or the delay of the signal. Other use of complex number is in the medical field. We use complex number to construct magnetic resonance imaging or CT scan imaging. We also use complex number to define an electromagnetic wave since it consists of electric and magnetic fields. And many other applications use the complex number. So let us first review some geometry and trigonometric property that we will use with complex numbers. If we have a triangle with one of its angle is 90 degree, then according to the Pythagorean theorem, the hypotenuse side, which is here A opposite to the 90 degree angle, this side A will equal the square root of the square of this side plus the square of this side. And if I take the tan of this angle, it will be the opposite side y divided by the adjacent side x. Now, if I want to find this angle theta, I will take tan inverse for both sides of this equation. So then this will be theta and this will be tan inverse y over x. Trigonometric property we will use is e to the power of j theta equal cosine theta plus j sine theta. So that's a complex number. Engineer use j. Physicists, other field, they call it I, but it's the same, j or I. Okay, let us start talking about complex number in its rectangular form and polar form and plot it as a vector. If we have a complex number a equal 4 plus j6, then this is expressed now in rectangular form, where the 4 is the real part and the 6 is the imaginary part. Now, if I try to plot this complex number as a vector, then I will move in the x-axis. This will represent the real part and the y-axis will represent the imaginary part. So I will move in the x-axis 4 units. Then I will go up 6 units in the vertical axis. And the vector will start from the point where I start until the point where I end. So that will be the vector A. Now this will be x and this will be y. Here it's equal 6 and for this example it's x equal 4. Now if I want to express this complex number in the polar form, then I will use the Pythagorean theorem. So I need to find the length of this vector. A. So that's the magnitude of the complex number. So that will be the square root, since this is 90 degree, of x squared, so that's 4 squared will be 16, plus y squared, so 6 squared, that would be 36. And this number should come up 52, and that will be 7.2. Now, if I need to find the angle here, theta, then I will be using this property. So theta will be tan inverse opposite, which is y over x, or basically the imaginary part here divided by the real part. So that would be tan inverse 6 divided by 4. And if you use your calculator, you should get 56.31 degree. If you express it in radians, then it will be 0.983 radians. Let's clean up. So now I can write vector A or complex A in polar form as follow. A equal the magnitude, which is 7.2 EJ theta, which is 56.31. Some textbook, to indicate this is a vector or complex, they put this bar on top of the letter A. Okay, what if you have the complex number expressed in polar form and you want to find what is it in rectangular form? Let's clean this. So now the question is, if you were given the vector A in polar form, so you don't know this, and you need to express this polar form in rectangular form. That vector A, the real part will be the x component. So the projector of this vector along the x-axis will be the real part, will be this. So the projection along the x-axis, which is this length, is A magnitude cosine theta, plus the imaginary part is the projection of this vector along the vertical axis. That will be A magnitude sine theta. And if you plug values, 7.2 cosine 56.31 plus j, the magnitude again 7.2 sine 56.31. And if you use your calculator, you should get 4 plus j 6. We could have get the same answer if we use this property. So this will be from here 7.2 cosine that theta, which is 56.31 plus j 7.2 sine theta. And that's exactly the same as this one. Let us take another complex number to show when the angle is negative. So let complex number B or vector B to be 4 minus j6. To plot this vector, so I move along the x-axis 4 units, then along the vertical axis minus 6 units, so that will be here. So the vector will be this one. And the magnitude of this vector will be the square root of the real part squared, that's 16, plus the imaginary part squared. You can include the minus, that's fine, but when you square it, it will be 36. You never include the j inside here, because when you square j, you get minus 1. So make sure you do not include this j when you calculate the magnitude. So that would be the square root of 52, which is the same as 7.2. So that's exactly the same as here. And we should expect that, because the magnitude of this vector is the same as the magnitude or the length of this vector. Now let's calculate the angle. So the angle of vector B, or let's call it theta, is tan inverse the imaginary, so that's minus 6 divided by the real, that's 4. And if you use your calculator, you will get minus 56.31. So that will be this angle, which is the same as this angle here, theta. Except this is positive because the angle above the x-axis. This angle here is negative because it's below the x-axis. And if I express this in polar form, it will be 7.2 E minus J 56.31. Now, this is a short review of complex number in rectangular and polar and vector forms. But there is one point that creates confusion to the student, which is the calculation of an angle if the vector is located in the third or fourth quarter of the plane. For example, let us find the polar form for the vector C equal minus 4 minus j6. Let's clean up. If we plot vector C, then we will be moving minus 4, that's 4 unit, to the left along the x-axis. So that's 1 unit, 2 unit, 3 unit, 4 unit. Then moving minus 6, that's downward, 6 units. So then this is the vector. Finding the magnitude is not a problem. The magnitude of vector C, that will be the square root, the real part square, plus the imaginary part square. And if you calculate these, that would be the square root of 52, and this will be 7.2. And that we should not be surprised because we know the length, the magnitude is length. This length is the same as this length. But if I want to calculate the angle, let's see. If I do it mechanically without taking into consideration the location of the vector, and they say the angle of C equal tan inverse the imaginary part, that's minus 6, divided by the real, minus 4. So that will be tan inverse. This minus and this minus will cancel, so you end up with 6 over 4. Look, this looks like this one here. So you plug this in your calculator, it tells you the angle is 56.31. And if I ask you to express this in polar form, you will write the magnitude 7.2 EJ, the angle is 56.31. But that's not correct. Here, vector C looks exactly like vector A. But we know they are different. A is here, direction this way, C is in this direction. So the mistake we did is the following. So when we calculate the tan inverse mechanically and plug in the calculator, it gives us this angle, which is this, which is the same as this angle. But the true angle is not 56.3 because the minus here and the minus here, that means the vector is in this quarter. So how do we resolve this problem? We add to 56.31 plus 180 degree, which is this whole thing, that angle here. So this angle plus this 56.31, that will be the true angle. So this vector above the x-axis by that much. So that angle will be then 236.1 degree. Another option, if you want to limit theta between minus pi to pi, or minus 180 to 180, then I will consider this angle. So instead of adding 180 to the 56.31, I subtract 180. So then theta will be 56, what the calculator gave me, minus 180, and that answer will be minus 123.69. So now this is this angle here. So you can use angle 236.1 where theta range from 0 to 360 degree. Or you can use this angle where theta range between minus 180 to 180. So plus 180, it goes this way. Up to minus 180, it goes this way. Let's clean up this a little bit. Now I can express vector C in polar form as follows. 7.2 EJ 236.1 or 7.2 E minus J 123.69. Both expressions are correct. If I convert these to a rectangular form, I will get this value. If I convert these to a rectangular form, I will get this also the same. Let's clean up. Same thing, if I have a vector D here equal minus 4 plus j6, and I try to plot it, I move 4 units this way and 6 units up, so the vector will be this one. Now, if you calculate the magnitude will be no problem. But if you calculate the angle, then the angle of vector D will be tan inverse imaginary divided by the real. And if you put this value in your calculator, you will get the same thing here, minus 56.31. And that's not correct. The angle between the x-axis and this vector here is this. It's not this one here. That 56.31 is this one. So that is wrong. So the correct answer, you add 180 degree to this value. So it will be minus 56.31 plus 180. And this will be 123.7. So vector D in polar form will be 7.2 EJ 123.7. So just remember the following. Rule of thumb, if you need the angle to be between negative pi or negative 180 and positive pi, positive 180, then add 180 degree to the angle of vector in the third quarter and negative 180 to vector in the fourth quarter. So you calculate the angle using your calculator, and if the vector in the third quarter, then add 180 degree. If the vector in the fourth quarter, then add minus 180 degree, as long as you want the vector or your answer to be between minus pi and pi. If you want your answer to be between 0 and 2 pi, then just add 180 degree if the vector here and 180 degree if the vector here to the value you get from your calculator numbers like this. Okay, so the next topic will be addition and subtraction of complex numbers. Let's say I have a vector A equals 6 plus J2. And if I express this vector in polar form, it will be the magnitude 6.32 EJ 18.44. And another vector B, 3 plus J 6. And in polar form, it will be 6.7 EJ 63.44. Now, if I want to add vector A plus B, so we will create a new vector or a new complex A plus B. The addition of two vectors, you add the reals together, so that will be 9, plus you add the imaginary together, so that will be J8. Now addition in the polar form cannot be done. We cannot just add this magnitude and this phase. That's not correct. So usually convert polar form to rectangular form and do addition and subtraction, and you're going to get a result. Then convert the result from a rectangular form to a polar form. Now, if we plot vector A, vector B, and vector C to see this addition, what does it mean? Let's plot first vector A. So vector A, we move 6 units in the x-axis and then 2 units in the y-axis. So this is the vector. And plot vector B. So that's vector B. And if we plot vector C, we move in the x-axis 9 and in the y-axis 8. So that will be. Graphically, I can get vector C without any addition. I can draw vector A, then vector B. Instead of drawing it from this point, I can draw it from here. So if I do this, then vector B is moving 3 units to the right and 6 units up. Vector B. It still has the same magnitude. This one and this one, they have the same magnitude and the same angle. So they are the same, except vector B, this one originate here and this vector originate here. So that's one way to look at it. Another way to look at it is the following. So let's clean up. If I complete the parallelogram that consists of this side and this side, then it will be something like this. And the diagonal of this parallelogram will be vector C. The diagonal that is between side A and B, not this diagonal. All right, let's now do subtraction. So let's clean up. If I want to find vector D that consists of vector A minus vector B. Then I can carry out the operation. So this will be A 6 plus J2 minus B, which is 3 plus J6. So that will be 6 minus 3, that will be 3. J2 minus J6, that will be minus J4. And if I plot this vector, I move 3 units in the x-axis and then down 4 units. So that will be this vector. Now I can think of it graphically as follows. 6 plus J2 minus 3 minus J6. 6 plus J2, I will be in this point. Minus 3, then I move 3 units, 1, 2, 3. Minus J6, I go down 6 units, 1, 2, 3, 4, 5, 6. So I am here. Let's clean up and think of it different way. If I draw this vector minus B, it will look exactly the same as this vector, but it changes its direction. So it will be minus 6, minus 3, so that will be this vector. Then if I draw the parallelogram of this side and this side, then it will look something like this. And D will be the diagonal between these two sides. Let's clean up. Another way to think of it is A minus B mean it's a vector that originates from the head of B to the head of A. So that will be this vector. And this vector is the same as this vector, except it's in a different location. The magnitude are the same and the angle are the same. This is minus angle, and here that's the same angle minus. So these are different way of looking at addition and subtraction in terms of vectors and plots. So what is important is the following. Addition and subtraction should be done in rectangular form. You cannot do it in polar form. So you have to convert from polar form to rectangular form, do the addition, the subtraction, and get the result. And if you need the result to be in a polar form, then just convert it from rectangular to a polar form the same way we did earlier. All right, let's do some multiplication and division. So let's take these two complex numbers, A equal 3 plus J4 and B equal 2 minus J5. Now I can carry out multiplication and division in rectangular form or polar form, but it's much easier if I do it in polar form. So if I find A in a polar form, that will be 5EJ 53.13 and B 5.39 E minus J 68.2. So let's carry out multiplication first in rectangular form. So A multiplied by vector B will be 3 plus J4 times 2 minus J5. Just like any multiplication, the real part of this multiplication will be these two components, the real of A times the real of B, so you will get 6, plus the multiplication of the imaginary part of A and B. And here you will get J4 multiplied by minus J5. The imaginary part will be the following, plus J. It's the real part of A with the imaginary part of B. So that will be 3 times minus 5 plus the imaginary of A times the real of B. So that will be 4 times 2. So when you carry out this will be 6 plus J times J is minus 1 times minus is plus. So that's plus 4 times 5 is 20 plus J 3 times minus 5 is minus 15 plus 4 times 2 is 8. So the answer is 26 minus J 7. Now if I carry out this multiplication in polar form, then I multiply the magnitude of A times the magnitude of B, EJ, and I just add the phase. And this should give us 26.95 E minus J 15.1. Now, is this value the same as this? Yes. If I find the polar form of this, then it will be the square root of 26 squared plus 7 squared. EJ tan inverse the imaginary minus 7 divided by 26. And this equal 26.95 and EJ minus 15.1. Same thing. Now, if I want to do division, again, division in polar form much easier. So let's do the division in polar form first. So let's say A divided by B. So in polar form, that would be 5 EJ 53.13 divided by 5.39 E minus J 68.2. So you divide the magnitude of A by the magnitude of B, and you should get 0.93. And the phase will be the phase or the angle of the numerator, 53.13, minus the angle of the denominator. And the angle of the denominator is minus 68.2. So the result is 0.93 EJ 53.13 minus time minus is plus. So this is 0.93 EJ 121.43. Now, if I carry out division in the rectangular form, it will involve more steps. So that will be 3 plus J4 divided by 2 minus J5. And usually to get rid of a complex number in the denominator, we multiply it by its conjugate. So conjugate means you change the sign of the imaginary part. And in the numerator, we will have this number. But since I multiply in the denominator this component, I have to multiply also here, same component. And then I carry out the multiplication in the denominator. When you multiply a complex number by its conjugate, you will always get the square of the real. So that will be the square of 2 is 4 plus the square of the imaginary. So that will be square of 5 is 25. Here I have to multiply. So 3 times 2 is 6. J4 times J5, that's minus 20. Plus J4 times 2, that's J8. 3 times J5, that's J15. So now the answer will be minus 14 plus J23 divided by 29. And if I carry out this division, now I can divide 14 by 29 and I will get minus 0.483 plus J23 divided by 29, that's 0.793. This is the answer in rectangular form, and it will be exactly the same as this answer in the polar form. The only thing you have to be very careful is finding the angle of these. The magnitude is simple. The magnitude will be the square root of this squared plus this squared. And the phase will be EJ tan inverse the imaginary divided by the real. If you carry out this operation, this quantity will give you 0.93 EJ. Now, if you carry out this in your calculator, you will get the following: minus 58.66. And this is different than this quantity. Why? Because that is not correct. Because if you plot this vector, it's somewhere here, minus 0.483 and 0.7. So it's this vector. So what you got, 58.66, is this quantity. So, but the angle is this. So then I take 180 minus this quantity. That will give me the correct angle, which is this. So I have to add here plus 180, since it's in the third quarter, as we said before. So then this answer will be 0.93 EJ 180 minus 58.66. You get 121.34. As I said, there is some rounding, which is okay. So division in polar form, much easier than division in rectangular form, which is all these. So addition, subtraction, you have to do it in rectangular form. Multiplication and division, do it in polar form. Okay, the next topic will be link complex numbers and sinusoidal signals like the sine wave and the cosine wave. Okay, let us link the complex number in polar form and rectangular form to the sinusoidal signals, the cosine waveform and the sine waveform. Consider the complex number A, whose magnitude is 1, and angle theta can be any value from 0 degree all the way to 360 degree. So basically it can be all the way 360 degree. So for example, if vector B equal 1 EJ30, that will be this vector. The magnitude here is 1 because this circle has a radius equal 1. Then the projection of this vector along the x-axis will be cosine theory, and that's the angle theory. So this is the x component of the complex number, plus j, the projection of this vector along the vertical axis. So that will be sine theory. So this length here is cosine theory, and this length here is sine theory. If I look cosine theory along this cosine waveform, the angle theory is here. This is the x-axis, is the theta. Then if I go up until this waveform, then the intersection along the vertical axis will be cosine theory. And cosine theory from this triangle is adjacent divided by the hypotenuse. And this is around 0.866. So this one here is this value. Now the projection along the y-axis represents the sine wave. So that is the sine wave. Again, I go to the angle theory and I go up until the intersection of this sine wave, and this amplitude of the sine wave at this angle is half. So this sine theory is opposite divided by hypotenuse. So that's half. And this value here is this one. So let's just take another example and do some cleanup. Let's take vector C, which is 1 EJ45. So that is this vector. And it will equal cosine 45 plus j sine 45. So the projection of this along the x-axis is this one, and the projection along the y-axis is this one. If I go in the waveform, 45 is here. So the value of the cosine function at this angle is this. So this is cosine 45. And that cosine 45, it's 1 divided by the square root of 2. And this is 0.707. So this is this value. And the same thing, if I want to find what's this sine 45 along the sine wave, angle 45, the value of the sine wave at 45, it's also the same level here, which is 0.707. So this is also the same here. So you can map any vector along this unit circle to the equivalent position in this waveform. A pattern that you can see is the following. Let's clean up. If I have a vector like this one, then the projection along the x-axis is 1. So that will be this point. And as the angle increase, the projection now become less. So now we are here. And the angle increase, the projection is even less. So we are somewhere here. And when the angle is here, now the projection along the x-axis is 0. So we are at this point. When it moves this way, now the projection is negative. So we could be in this point, negative. The projection is more negative. So we could be here until it is here. Now the projection along the x-axis is negative 1. So now we are here at pi. So this is pi and the projection is negative 1. And if I keep going here, now the projection is still negative, but it becomes less, and here even less until here. That will be 0. And when the vector go 360 degree back, that will be this point. And the same thing, we can follow the projection of a vector of different angle along the vertical axis and related to the sine wave. So if we have a projection, a vector here, then the projection along the vertical axis is 0. So we are here. Okay, so sometimes if you can visualize this triangle and this waveform, then you can find EJ for angle 0, 30, 45, 60, 90, and so forth without even using the calculator. In DSP, we use this concept by plotting the poles and the zeros of the digital systems. For example, you may have 2 poles here and you may have 2 zeros here. And this unit circle will represent omega, which is a digital frequency. So if I want to know what's the system response to a frequency located here, that could be omega 0.3 pi. In this case, the system response will be the length of the vector from this 0 and this 0 to this point. So that will be R1, R2 divided by the length of the vector from the poles to this frequency of interest. And this is D1 and D2. So the system response will be R1 times R2 divided by D1, D2. Basic concept of complex and sinusoidal help us to understand how the system responds to different frequencies. Okay, let us carry out some operation with complex number in a real function. This function could be a time function and can represent the impulse response of a system. So h of t equal 3 plus j4 e minus 1 plus j2 t plus 3 minus j4. Now this function has these two complex numbers in rectangular form and they are conjugate of each other. And this complex number is multiplied by a function of time that has a complex number, which is this one. Since h of t is a real signal, it should not have a complex number. So let's see how we can rewrite this function to eliminate any imaginary part inside this function like j. So the first thing we will do, we will convert these complex numbers to a polar form so we can multiply it by this function. So the magnitude of this one will be the square root of the real square 9 plus the imaginary, and the angle or the phase of this one will be EJ tan inverse the imaginary divided by the real. And then I will write this as it is. Now I will delay writing this here. I will just continue the operation here, then I can easily fill this part. So the magnitude here, 5 EJ, the angle, if I use the calculator, it will be 38.66 degree. Now I will break this function to two parts. First part will be E minus 1 time t, E minus t, time E, J2 time t, that will be J2t, plus. Let's clean up first. Now this is a conjugate of this complex number. That means it will have the same magnitude and the angle will be negative. So I will have for this one 5 E minus J, 38.66. And then I will break these to two parts, E minus T, E minus J 2T. Now I will take this component as a common factor between these two terms. So what's left from this term is the following. And from this term, the following. I will combine these two as follows. And these two as follow. This kind of procedure, you will be doing it in many courses to simplify a signal to a real signal instead of having complex component and j. So now notice the following. These part look similar to a function in trigonometric that we are familiar with, ej theta plus e minus j theta over 2 equal cosine theta. So you can think of everything here as theta and here minus theta. So I need 2 in the denominator. So I'm going to divide this term by 2 and multiply here 2. So then this will be 2 times 5 is 10, e minus t, and here I will have 2. This will come down. And this term now will be cosine 2t plus 38.66. And this is h of t. So this is a real function, has no j, no complex number in it. And if I plot it, it will look something like this. And this, you will see it in many courses, as I said, where h of t could be the impulse response of the system. So if you excite a system with an impulse, the output will be this one. This is the end of this video, and thank you for watching.